developed economy is heavily leaning towards the eradication of single-use plastics as a step towards a sustainable community. The usage of paper bags, eco bags, and other reusable or biodegradable bags have been implemented in several cities in our country in support of this. Our study focuses on using the starch from Sandakan banana as an alternative component, as it is one of the major sources in developing bioplastic according to Zhang in 2012. This specific species, scientifically identified as Musa x paradisiaca L, was chosen due to the presence of homoglycan polymer according to Eggleston et al. In 2018, and its abundance in our locality here in Dipolog City as well as the country, making it a cost-effective product which can benefit the community, the environment, manufacturers, users, and future researchers. This study aims to produce a Sandakan starch bioplastic or SSB and compare its quality with a commercially sold plastic or CSB. Specifically, this study sought to know the quality of the produced SSB in terms of water uptake, biodegradability with soil burial, river water immersion, and seawater immersion as its subparameters, and tensile strength. It also seeks to know the significant difference in the quality of the produced SSB as compared to CSB with the same parameters. This study covers the production and evaluation of the quality of the produced bioplastic and applied post-test only control group design, where the experimental group is the produced bioplastic and the control group is a commercially sold plastic. To extract the starch, 47 kilograms of unripe Sandakan banana was collected, washed, peeled manually, and scaled. 3 kilograms of sliced banana flesh was added to 4,500 ml of distilled water and blended thoroughly for 2 minutes. It was then placed into a container after being sieved and was stored to be decanted for 3 days. A heterogeneous mixture was formed, of which the components that settled at the bottom were starch. The starch granules were placed on a tray and sun-dried, which formed clumps of starch granules which were then powdered with a pestle. To produce the bioplastic, 15 grams of the dried Sandakan starch was added with 150 ml of distilled water in a 500 ml beaker. 8 ml of glycerol was added as plasticizer and stirred. It was cooked under low fire on an electric stove, stirred constantly until the mixture turned into an opaque gel with a brown color. It was spread on a 6x5 inch molder and sun-dried for a day. The sheets were cut into 1x2 inch to use for water uptake and biodegradability test, and 1x3 inch for tensile strength. 15 replicates were used for each parameter for a total of 80 replicates. To test the water uptake, 15 1x2 inch replicates were pre-weighed, then soaked in a 500 ml beaker containing 250 ml of distilled water for 24 hours and was procured from the water using forceps and weighed again. The same procedure was done for the commercial plastic. The following formula was used to compute. To test the biodegradability, 15 1x2 inch samples of SSB were used for each subparameter. Seawater, river water, and soil were collected from locations within the city. The replicates were pre-weighed before being buried or soaked for 19 days, extracted, and weighed again. The same was done with the CSB. The following formula was used to compute. To test the tensile strength, one 1x3 inch SSB replicate was placed securely between iron clamps with laboratory weights weighing 100 grams, 200 grams, and 500 grams placed on top of the bioplastic with an interval of 100 grams added per minute, ending once it was ripped. The same method was used to test the CSB, and the following formula was used to compute. Results revealed that the produced bioplastic is superior to the commercially sold plastic in terms of water absorption, tensile strength, and biodegradability, namely soil burial, river water immersion, and sea water immersion. Using SPSS student trial version, one-way ANOVA was employed. In conclusion, the component used in the production of SSB can absorb water, can biodegrade in soil, sea, and river water, and can withstand force. The Sandakan starch implied to be an alternative component in making bioplastic since it has a superior water uptake and mass reduction compared to commercially sold plastic. The significant values are 0.000 for water uptake and biodegradability and 0.033 for tensile strength. Since it is less than the alpha 0.05, the null hypothesis was rejected, showing a significant difference between the quality of the produced bioplastic from the commercially sold plastic, and that the starch from the Sandakan banana can be used as an alternative component in making bioplastic.